All right, this is our Aerodynamics project for Dr. Batia's fluid mechanics class. I'm Jack Terafay.
I'm Sebastian Marschlach.
I'm Ryan Megan.
I'm Braden Brusso.
I'm Nicholas Chella.
To start with our executive summary, at a speed of 150 miles an hour, we were able to max out our lift-to-drag ratio at negative 4.97. This came from a lift force of negative 14,747 newtons and a drag force of 2,967 newtons. Next, we're going to start talking about our design approach and the inspiration that went into it. For starters, with profile, our main inspiration for this was the Mazda 787B. This was a Le Mans prototype that raced up until 1992 when it was officially banned due to its rotary engine. As you can see, though, the main takeaway from this, as outlined in red, is that the height is very small, is a very squatty vehicle with the wing below the max height limit, which we kind of kept as a design parameter when considering designing our own rear wing / spoiler. Next, we wanted to take a look at how we should design fluid flow for the overbody of our car. Starting left to right, we have the Ferrari 499P. This is a 2023 Le Mans prototype model. It actually won the most recent Le Mans race in 2023. And the main takeaways from this were the side pockets outlined in blue around the side of the driver, which allowed for air to slip around the vehicle, as well as the closed cockpit design outlined in purple and how it smoothly distributes the airflow around the sides of it, as well as over the top into the rear spoiler / the air intake at the top. And another interesting design consideration from this model was that the side along the tires actually dips down and then goes back up over the rear tire. We experimented with this, but found that this design really was not adequate for helping us decrease drag, and actually overall just didn't really decrease drag and didn't really help with our downforce. Moving on to the Audi R8 LMP. This is one of the most successful cars ever made that raced in Le Mans. The main takeaways from this car, and really our car took a lot of design inspiration from this. If I had to pick a car that was the most influential in our design, it would be the Audi R8. As you can see, the outline in red, there's a lot of ways for air to come over the top of the vehicle, creating regions of high pressure. This would create larger pressure differentials, which creates more downforce. The air is able to flow around the sides of the car very nicely and slip into these air intakes. And as you can see, I've outlined in gray over the middle, if we're able to somehow point out the nose and kind of like create a nice sharp shape, it'll help additionally distribute air across the sides of the vehicle. The last thing I wanted to take away from this, which will help us transition to our next topic, is how severe the wing is. The wing really kind of creates this nice cup shape that helps distribute air that goes into it up across the wing, which creates lots of downforce, and this was something we wanted to explore with some other prototypes as well. The next step we wanted to look at was how ground effects can play into our vehicle design. The two cars I picked for this specific topic were the Peugeot 9X8 and the Lotus 79 Formula One car. Starting with the 9X8, I outlined in a box in red is a note that says we did not want to add a rear wing, which is interesting because a lot of these Le Mans prototypes include wings. So that means that they must be generating their downforce elsewhere. And as you can see from this rear view, they have a really severe diffuser along their back, as well as really thick plates outlined in the lower blue box that keeps the air attached to the sides of the diffuser for as long as possible to allow the air to smoothly transition back out the end of the vehicle. They have very high ground clearance, as you can see with the red arrows, the red vertical arrows along the back. We wanted to incorporate this somehow, create large space out of the back of our vehicle to allow the air to escape a lot easier. Some other things I have outlined here are in blue on top. These were the panels along the sides of the car, which keeps the flow, again, attached like it does along the bottom. This was good to allow the air to actually make contact with their own rear wing, which as much as they say they don't want one outlined in green, they have a little slope that kind of helps generate downforce by pushing air up and out of the vehicle. And these two combine nicely to create as much downforce as possible. And then moving over to the Lotus, this is one of the most famous examples of downforce used in motorsports. The severe design between the ground and the expansion space is something we really wanted to explore along the sides of our engine block, which you will see later. The main takeaway from this is how to gradually bring the air that you sped up quickly along the bottom of the car to the diffuser and then out the back of the car. The final design inspiration we took was for the rear wing slash long tail design of the race cars. The two inspiration points that we took was from the Porsche 956 as well as the McLaren F1 GTR long tail version. While starting with the Porsche, this is one of the most successful cars to ever race. As you can see, a lot of the aero designs in blue we kind of kept in the back of our minds is how to keep air slipping around the car as best as possible. But the main takeaway from this was how the air stays attached to the spoiler. They use these large panels outlined in green to keep flow attached, and then have a very gradual slope along the top outlined in the in the yellow arrows. So you can see the fluid flow comes across it very smooth, very straight, and then the underside is extremely severe. It is cupped similar to the Audi R8 spoiler. To allow the fluid to speed up quickly along the bottom, creating a large pressure differential and a lot of downforce. Moving over to the F1 long-tailed GTR, this is one of the greatest cars ever made, period. And as you can see, it's a very slippery car as well. Air is able to move around the car very quickly, especially with the nice gradual from low to high towards the spoiler in the back. But some of the takeaways we wanted from this were, as well as the spoiler design similar to the Porsche, they have a multi-stage spoiler that has really 4 stages you can pick out, one along the bottom for the fluid that stays attached, one for along the side of the car, one that stays along the rear of the car at stage 3, and then, of course, whatever is able to hit the spoiler is stage 4, and we wanted to incorporate something similar to that in our design. And now moving on to our real design and initial design of the car, this was a low drag slipstream version of what we were looking to accomplish. Going forward, I have outlined in green good features, yellow okay features, and red bad or ugly features that I really wanted to change from the designs. So starting here, we're able to get a lot of good slip stream around the car. That's why I named it such. Fluid flow is able to move quite quickly across the car as well as along the top surface, but it had a lot of problems, especially looking at the first yellow region with the 2 lines that travel along the length of the car. They were flat, so they really weren't helping us generate any downforce. And the bottom of the car really was flat too, not really helping us create a large pressure differential or creating a nice rear diffuser. Some of the really bad aspects of this car were the sharp edges at the front, which allowed fluid flow to detach quickly off of the front end of the car, as well as the fact that there is absent of a rear wing or some sort of lip that helps push air upwards and creates downforce. We really had no use for the air that was coming off the back of the car. As you can see, it just would kind of escape and do nothing for us, as well as air would escape from out the side of the tire and just kind of detach and not really serve any use for us. Which is why this design needed lots of work overall and needed a large overhaul moving into design 2. Design 2 was a great improvement on the first design. This is what I've labeled as a more downforce efficient model. The lines that were originally flat, as you can see, I've labeled as now a curve, and the underbody is very, very severe with the diffuser that it creates. This helped with a very nice pressure differential, as well as bringing the air back up to the spoiler that is now gigantic in the back. Which had its own problems, and I can move on to that now. The fluid flow would kind of come over to this spoiler, and it would kind of get stuck, and it would really, really shoot up. So we got a lot of downforce. As you can see, we had about 13,000 newtons of downforce just from this initial design of a spoiler. But a lot of the major issues still remained of drag. This car was regularly pushed the limit on drag, and we were routinely over with that limit. As you can see, air kind of just hits into it, and it doesn't really do anything. If it does, and it has to wait to be pushed out, as well as the back end still has fluid flow detaching from underneath the car and not being used by the spoiler, which increases our drag and our pressure differential regions in the back, as well as just kind of does not serve any purpose for us. The front spoiler became a little bit more smooth, a little bit more, or front splitter, sorry, became a little bit more downforce efficient, but it still detached fluid flow along the sides, creating and not allowing us to best utilize all the fluid flow that was coming across the car. Moving on to one of the more improved designs that we were able to accomplish was the LIV1A, which I named because I believe this would be our final version, but we ended up making even further improvements. I'll start with the bad. The drag was still very severe. We decreased the size of the wing. As you can see, the original wing was actually at max height. This one we tried to bring down a little bit more to reduce the drag and the cross-sectional area overall, but it still had problems of hitting into the wing and kind of stagnating still, especially with all these slits and slot regions. It really wasn't efficient in drag, but did produce a lot of downforce. This was our first time our lift-to-drag ratio improved above 3.5, which was extremely important, but we still lost fluid flow across the front of the car in yellow. It still kind of did not curve around the car like we wanted, but major improvements were made along the front of the car as well as the bottom. We kind of combined the previous two designs by keeping a very smooth flat region across the bottom, which then, like the Lotus Formula car, then we gave up into a diffuser, which led to our rear wing, and we closed off the back end outlined by the dotted green line on the back. We smoothed the front of the car and rounded it to allow fluid flow to better go across the front, like the Audi car previously, and we smoothed out the front of the car as well as some of the driver components, which we still left at the radius intact at 10 inches, but then we smoothed out the rest before it, just that way we were able to decrease drag by a little bit. Overall, this was a better design, yet we still felt there was more improvement to be had. And at last, we reach our final design, the 2B design, which called for a complete overhaul of the rear wing. Getting rid of that giant bulky wing, we were able to implement something that was a little bit smoother and a little bit more drag efficient while also producing significant downforce. We made it match the height of the car, so that way we reduced our cross-sectional area even more. As well as we created this little combo spoiler feature in the back where air gets scooped into it and then combines with the air that crossed over the top of it, creating large pressure regions across the top. And then in the lighter lime green, we created a very severe back scoop, as you can see in picture 2 as well, that accelerates the air across the bottom of it, creating a better pressure differential overall with a more efficient design. Something we also changed is we rounded the front ends of the car, allowing fluid flow to better stay attached along the sides. This helped decrease the drag overall of the car. We also optimized fillets so that way our drag was decreased as much as possible. And we also settled on a final very straight flat design along the little side pockets of the car. And then, as you can see in picture 2, how the rear diffuser works, where fluid flow over the engine block and passenger compartment is very fast and accelerates and then hits our diffuser and then gradually gets brought back up to our spoiler, adding to more downforce and reduction of drag overall. We ended up with this car reaching our lift-to-drag ratio of negative 4.97, and overall feel that this is a very solid and extremely optimized design. So now that we've kind of reviewed over the design concepts, I just wanted to bring this into SolidWorks itself and kind of show you around the car and move it around so you can see some of the features a little bit better. So we'll start with the front of the car, and as you can see, it is very smooth, or as relatively smooth as we were able to get it to eliminate drag along the multiple slopes along the car. As you can see, we're also generating a little bit of downforce in this region specifically here, as well as down here due to our upward slope shape. Same with the two side wings here. They're also generating a little bit of downforce with minimizing drag due to their sloped design this way. It allows air to curl around it and stick to the car, better keeping flow attached to the car and decreasing drag. As we get over top of the car, nothing really changes. It's just straight line to the to the spoiler. We're trying to gradually bring a lot of air, trying to increase pressure here and gradually bring it up to speed over to the spoiler as well. And then, as I said, we get to the back of the car and we have a sort of double spoiler design with a very big scoop, as you saw in the Audi R8. As I pointed out, very big scoop to generate a lot of downforce. There's a lot of low velocity, high pressure in this region. And then it will funnel into what I believe is happening is it will funnel off of this, kind of ramp up, and then the air that comes across the top of the car that doesn't get sucked down in comes across the top, hits into this spoiler, keeping that pressure high and even more pressure because it's grabbing more air across as it goes, creating a higher pressure region here, which then when we turn to the back of the car, just position it really quickly, we then see a more severe rear end of the spoiler, which allows the air to move quicker, therefore creating a low pressure here, getting our downforce pressure differential that we were looking for. Underneath the car is kind of the same story, keeping it as close to the ground as possible, having air squeeze through here, keeping it quick, keeping a low pressure region here, trying to gradually bring the air back up here and help it diffuse out as it gets along the length of the car. and then of course hit into our double spoiler, also help generate downforce, keeping the flow attached within the car so it doesn't just spray out, along with these little side skirts in the back, and of course filleted edges to keep drag as low as possible. And each one was optimized with comparing simulations lift and drag ratio. So before we move on to a flow sim, I'm just going to quickly turn this on. Show. Okay. And I wanted to review the drawings of our car. So I'm going to start with this sheet here, which kind of just gives over the general overview of our dimensions. I'll start with the top view and then I'll work around and end in the center. So starting with the top, once again, you're going to see these dimensions a lot, but we have our length of 185 inches, 80 inches, and I should mention all these dimensions are in inches as defined by the sheet. And then, of course, our engine block, which sits just about here, or sorry, passenger block and engine block, which is about here, are both 35 inches. The engine block was not required to be 35 inches long, but it just helped keeping flow straight and, comfortably situated along the side of our car up into the spoiler. Going along to here, our height is within spec. It is at max 39 inches. We had a max of 45. I'm trying to keep this as low as possible. I had mentioned, just at the top of along the car. We then get to the tires. The first dimension you'll see of the tires is that all the widths are 12 inches, along with a 4-inch ground clearance along the entire back of the car. Same thing with this tire, 12 inches in diameter, or I'm sorry, in thickness. Then we'll move to the bottom of the car. Once again, length is still consistent, and the width of the car is still consistent with the tires situated. As you can see here, the edge of the width, this is just the fillet along the bottom of the car, tire that the drawing is picking up. Once again, this is the compartment for the passenger compartment in the engine block, and it's maintained to the width of 35 inches. Moving along to the front of the car, once again, just maintaining that ground clearance is all this is trying to prove. These two radii here are proving that this is the top of the engine block and passenger compartment, and that they are both held to a consistent 10 inches as per requirement. And then ending here, just to prove, we have a wheel diameter of 28 inches for all wheels. This is just representing both one side, but it works for both sides. And I'll zoom in here just so you can see. This is the top edge of the fillet along the side of the tire, and it just stays within the bounds of our vehicle. Once again, more fillet, just proofs of the engine block, our passenger compartment as well as the engine block, and then our wheelbase width of 104.3 inches. And just before I go from the drawing, I wanted to pull up a section view here of the car. So once again, we're going to start with the front view, and I'm just cutting along the center so you can see through to the side. And this would be the passenger compartment in green and the engine block in red. Once again, maintaining that fillet radius, as you can see here, of 10 inches on top, 10 inches on top. And then we can get into some more of the nitty gritty details with their dimensions. Like I said before, both are just held to 35 inches, which is satisfied for both because we had a minimum restriction for the engine block of 30, but keeping it at 35 does not change that requirement, because it should just fit within that dimension regardless. We have a total length of the passenger compartment of 50 inches and a 40 inches for the engine block per requirement. The passenger compartment goes from the bottom to the top, and it's 35 inches tall with that 4-inch ground clearance, which makes up our total height of 39 inches as verified. And then we get closer here to the engine block, and I just wanted to point out we have this little back diffuser, as you saw in the Lotus, similar to the Lotus Formula One car, and it is just exactly tangent to it here along this edge, creating just enough clearance for our engine block to rest comfortably. And then lastly, I just wanted to quickly come over here and run a flow sim for everybody, just so that they could see our drawing at work. I'm going to turn off this surface plot I have here really quick. And let me bring back in the ground plane, unsuppress the ground plane. So let me first start with how the car is situated within here. I can go over to here and show our constraints with our mates. The car sits tangent with both tires, just that way it is situated along the ground plane. It is held with a width constraint, centering it along the width of our ground plane, and the dimension of our ground plane is 3 times the width of the car. So situating it in here, you get 1 car length on this side, 1 car length on the other side. And then we have a distance constraint, which I just want to open up and show that we are exactly 185 inches away from the front of the car, which puts 1 car length in front. And then the ground plane is dimensioned to have 4 car lengths, which leaves 2 behind the car as seen by this large area here. And the last one, which I might have questions about, but I wanted to verify, is that the height of the bounding box looks small, but the reason I turned that sketch on before is this line here is exactly 2 car lengths high. It is 39 inches times 2. So it keeps the bounding box situated just at 1 car length above, which helps in our calculation, keeping it extremely precise. And then, as you can see, the bounding box clips into the ground plane and is situated at the edges of the ground plane as well, creating a proper simulation bounding box. So let me just hide this sketch really quick, so that way you can just see the car and there's no obstructions. And then let me come back over here to the flow sim. And I wanted to verify the parameters as well. So let's start with the general settings here. Fluid flow, external, come down to fluids. We have air, it's defined. And then we want to come here to wall conditions, no wall conditions. And we have our velocity here. This is just 150 miles per hour converted to meters per second. Okay, everything looks checked out, and it was verified to be running in the positive x direction points this way. So our flow will be running across the car like this, and I will pull up a velocity flow field afterwards just to verify that. So let's run the simulation. Before I do that, actually, show global mesh as well. Edit definition, just to prove that we're on 4 here. Yep, definition of 4. Looks like we are all set to go. So mesh, new calculation, run. Just wait here for this to run. I guess in the meantime, while this is running, I can sort of explain some more design constraints we went for. Of course, we could have made this more severe in the front here and cut this fillet off a little sooner, but we ended up cutting into our engine block, which would have been illegal. We paid very close attention to making sure that fillets were coming outwards and not digging into the engine block and passenger compartments, because that would reduce their overall size and therefore put the car out of spec. Yeah, it was just another major design constraint we wanted to make sure we considered. Okay, so at about 121 iterations, as you can see there, it's our simulation was complete. It stopped, and now you can see our results are loaded along the side here. First, from both the surface parameters, this just shows the forces along the car. So we can see our x comp of the force, y comp of the force. And then along here, you see I have this goal plot. One of the other students in this class helped me create this equation plots where I'm able to just quickly divide the y comp of the force by the x comp of the force. And this creates our lifted drag in a quick 2-click process. And our lifted drag was a little bit lower than we reported, but we've had results waver between anywhere from negative 4.95 to negative 4.97. So we reported our highest value to the class. And let me just close all this, and I can show you a flow field. Let's see, there we are. And let me just get this to run really quickly. So you can see flow is staying attached, like I said, on the side of the car. We're getting some low pressure regions here, high velocity. Of course, this is a velocity plot along the car here. It comes up here, and then I was saying, as we said here, creating that low velocity, high pressure back here. And then, of course, I can show you the turbulent flow coming off of the back of the car. If I can just go normal to this. Okay. So I'm going to pass this off to one of my teammates, and they are going to continue more about the plots that you're seeing here. They're going to talk more about the lift to drag ratio at speeds, as well as the pressure and velocity along the car.
For our first plot, we graphed drag force and downforce versus vehicle velocity. Our drag force and downforce was in pounds, and our vehicle velocity was in miles per hour. Starting from 50 miles per hour, we had about 70 pounds of drag force and 360 pounds of downforce. And we graphed it all the way up to 200 miles per hour. At 200 miles per hour, we had about 1,100 pounds of drag force, and we had over 5,000 pounds of downforce, meaning we gained a lot of downforce without gaining a lot of drag up until 200 miles per hour. For our second plot, we graph lift to drag ratio versus vehicle velocity miles per hour. All the way from 50 miles per hour to 200 miles per hour, our lift to drag ratio remained pretty constant. It was in the negative 4.9 to the negative 4.5 range throughout the whole vehicle speed. For our third plot, we graphed aerodynamic horsepower versus vehicle velocity. At about 50 miles per hour, we needed about 9.8 horsepower to overcome the drag force, and at 200 miles per hour, we needed over 590 horsepower to overcome the drag force, which means the horsepower required goes up exponentially as you go up with speed.
So this is a pressure plot of our car in an isometric view when it's traveling at 150 miles per hour. The scale ranges from 97,000 pascals, pictured in blue, to about 139,000 pascals, pictured in red. And then this is our car under the same pressure scale, but for a front isometric view. And this is a pressure distribution for a rear view under the same pressure scale. And lastly, a pressure distribution for the bottom view with the same pressure scale.
For our air velocity analysis, we analyzed the slice plot along the center line of the vehicle when traveling at 150 miles per hour. The scale of our velocity ranged from 0 meters per second in the dark blue all the way up to 91 meters per second in the dark red. In addition to the center line, we chose to make an additional analysis point along the side rails, since they are a different shape than the center line we analyzed. This analysis followed the same velocity scale from 0 to 91 meters per second.
In the testing process, it's possible to test a 1/20th scale model of the full-size car in a water tunnel. In finding the velocity at which to run the water tunnel, Reynolds number was first calculated for the model at full scale in a wind tunnel, resulting in a Reynolds number of 21,518,166.7. To observe the water tunnel, Reynolds number was calculated for the car at 1/20th of its original size. In performing this calculation and the density and viscosity values, the air were changed to those of water, and the car's original length x was reduced to 1/20th of its original size. The Reynolds number equation was solved for v sub s, with v sub s representing the unknown velocity of the car moving through the water tunnel. V sub s was determined to be 91.75 meters per second, or 205.23 miles per hour. To determine the lift, in this case downforce, and drag force values recorded in the water tunnel, the ground plane and car design were scaled to 1/20th of their original sizes with respect to the centroid of each component, and calculated using the same methods as in the original calculations of lift and drag force. As the calculations were computed in SolidWorks, the scale feature was used to reduce the size of the car and the ground plane, with their respective mates maintained, and the distances of the car from each edge of the ground plane reduced to 1/20th of their original sizes as well. As such, when recording in the water tunnel, drag force was found to be 6,539.2 newtons, and lift was observed as negative 28,685.3 newtons, with lift to drag ratio being negative 4.38. These values can be compared to the original calculations for the car at full size and wind at 67 meters per second, where drag force was found to be 2,967.1 newtons. Lift was found to be negative 14,746.9 newtons, and lift to drag ratio was found to be negative 4.97.